Welcome to a webcast made by the Learning Enhancement team based in the Dean of Students office at the University of East Anglia. This webcast is part of the Steps into Complex Numbers series and concerns the basics of complex numbers. This guide introduces complex numbers and describes their definition and notation. It also shows you how to add, subtract, multiply and divide them, and defines the complex conjugate. Introduction. It is common to learn at school that you cannot have the square root of a negative number. This seems to make sense as the square of both positive and negative numbers are both positive numbers. For example, both 3 squared equals 9 and minus 3 squared equals 9. This implies that the square root of 9 is both 3 and minus 3. Given this, the question, what number do you square to make minus 9, seems impossible to answer, as the square of both 3 and minus 3 is positive 9. You can write this question mathematically as x squared equals minus 9, and accept that this equation is impossible to solve. However, mathematicians are always looking to solve equations that are seemingly impossible or difficult. The answer to how to solve such equations, and many others, is one of the most important, profound and controversial discoveries in the field of mathematics. It has its origin in the solution of certain types of cubic equations where the square root of negative numbers were evident in the method but conveniently cancelled out. Over time, the idea of a square root of a negative number was accepted by mathematicians and was called an imaginary number. A new number was defined as I equals the square root of minus 1, or equivalently, I squared equals minus 1. So I is the square root of minus 1 and I squared is minus 1. Any number which contains I is called a complex number by mathematicians. The existence of I allows you to write and work with the square root of a negative number without assuming that it is impossible to do so. This has proved extremely useful in pure mathematics, and especially in physics, where the solution of many fundamental equations involve complex numbers. Note, although I is commonly used, in the study of electronics J is used instead, as I represents current. Example, solve x squared equals minus 9. Taking the square root of each side gives x equals plus or minus the square root of minus 9. The answer is the square root of a negative number. As minus 9 equals minus 1 multiplied by 9, you can use the laws of indices to separate the root into the square root of minus 9 equals the square root of minus 1 multiplied by the square root of 9. As the square root of 9 equals plus or minus 3, and, as you have just seen, the square root of minus 1 equals I, the answer becomes x equals plus or minus the square root of minus 9, which equals plus or minus 3i. This example illustrates an important point. There is no need to define an infinite amount of new numbers to cope with the square root of a negative number. You only need I. This is because, for any negative number, negative n, the square root of minus n equals the square root of n multiplied by minus 1, which equals the square root of n multiplied by the square root of minus 1, which equals the square root of n multiplied by I. How do complex numbers relate to other numbers? There are various ways to write a complex number. This guide will concentrate on the Cartesian form of a complex number. It is very common for a complex number to be called z, and in Cartesian form z is written z equals a plus bi. This is the Cartesian form of a complex number, where a and b are real numbers. See study guide, different kinds of numbers, for more details about real numbers, and have special names. A is the real part of z, often written like this. So, the real part of z equals a. B is the imaginary part of z, often written like this, so the imaginary part of z equals b. It should be emphasised that the imaginary part of a complex number is the real number that is multiplied by I and does not contain I. When a equals 0, z equals bi and is called an imaginary number. When b equals 0, z equals a and is a real number. Example: what are the real and imaginary parts of the following numbers? A, z equals 5 plus 3i. B, z equals minus 2 minus I. C, z equals minus 6i. D, z equals 3.4. In part A, the real part of z equals 5 and the imaginary part of z equals 3. In part B, the real part of z equals minus 2 and the imaginary part of z equals minus 1. Remember to include the sign in your answer. In part C, this is an imaginary number, so the real part of z equals 0 and the imaginary part of z equals minus 6. In part D, this is a real number, so the real part of z equals 3.4 and the imaginary part of z equals 0. Sometimes a complex number is not expressed exactly as z equals a plus bi, and it is useful to manipulate the number to help you determine the real and imaginary parts. Example: solve x squared plus x plus 1 equals 0. This is a quadratic equation and you can use the quadratic formula to solve it. See study guide solving quadratic equations using the quadratic formula for details. This gives x equals minus 1 plus or minus the square root of 1 minus 4 all divided by 2, which equals minus 1 plus or minus the square root of minus 3 all divided by 2, which equals minus 1 plus or minus the square root of 3 multiplied by I all divided by 2. So the two solutions are x1, which equals minus 1 plus the square root of 3 multiplied by I all divided by 2, and x2, which equals minus 1 minus the square root of 3 multiplied by I all divided by 2. However, as the solutions are complex numbers, it is useful to separate the real and imaginary parts to express them in Cartesian form, as z equals a plus bi. For x1, x1 equals minus a half plus the square root of 3 over 2 I. You can see that the real part of x1 equals minus a half and the imaginary part of x1 equals the square root of 3 over 2. For x2, x2 equals minus a half minus the square root of 3 over 2 multiplied by I. You can see that the real part of x2 is also minus a half, but the imaginary part of x2 is minus the square root of 3 over 2. When the discriminant of the quadratic formula is negative, you will always get complex numbers as solutions for x. The complex conjugate. Every complex number has another complex number associated with it, called its complex conjugate. The complex conjugate of a complex number z is written as z bar, or often as z star, and is found by changing the sign of the imaginary part of a complex number. So, if z equals a plus bi, then z bar, its complex conjugate, equals a minus bi. Example: what are the complex conjugates of the following numbers? A, z equals 5 plus 3i, b, z equals minus 2 minus I, c, z equals minus 6i, and d, z equals 3.4. A. If z equals 5 plus 3i, then the complex conjugate z bar equals 5 minus 3i. B. If z equals minus 2 minus I, then the complex conjugate z bar equals minus 2 plus I. C. If z equals minus 6i, then the complex conjugate z bar equals 6i. D. If z equals 3.4, then the complex conjugate z bar also equals 3.4. The complex conjugate of a real number is the number itself. You should also notice that the solutions to the quadratic equation in the example in the previous section are also complex conjugates of each other. In fact, when the solutions to a quadratic equation are two complex numbers, they are always complex conjugates of each other. Adding and subtracting complex numbers. Adding and subtracting complex numbers is relatively easy. You simply add or subtract as necessary the real parts of the numbers to find the real part of the answer, and add or subtract the imaginary parts of the numbers to find the imaginary part of the answer. Example: if you have two complex numbers, z1 equals 5 plus 3i and z2 equals minus 2 minus I, what is A, z1 plus z2, and B, z1 minus z2? A. You can write z1 plus z2 equals 5 plus 3i plus minus 2 minus I. Adding the real parts gives the real part of the answer. 5 plus minus 2 equals 3. Adding the imaginary parts gives the imaginary part of the answer. 3 plus minus 1 equals 2. So, z1 plus z2 equals 3 plus 2i. B. You can write z1 minus z2 equals 5 plus 3i minus, open bracket, minus 2 minus I, close bracket. Subtracting the real parts gives the real part of the answer. 5 minus minus 2 equals 7. Subtracting the imaginary part gives the imaginary part of the answer. 3 minus minus 1 equals 4. So, z1 minus z2 equals 7 plus 4i. Multiplying complex numbers. You should know that a complex number has two parts, real and imaginary, and this complicates their multiplication. However, it is the same as opening brackets with two terms in each, and in order to multiply complex numbers successfully, you should employ a method which opens such brackets. The study guide, opening brackets, illustrates a grid method. Example: if you have two complex numbers, z1 equals 5 plus 3i and z2 equals minus 2 minus I, what is z1 multiplied by z2? You can write z1 multiplied by z2 equals, open bracket, 5 plus 3i, close bracket, multiplied by, open bracket, minus 2 minus I, close bracket, which reveals the reason why you need to open brackets to find the answer. So, z1 multiplied by z2 equals 5 plus 3i multiplied by minus 2 minus I, which equals minus 10 minus 6i minus 5i minus 3i squared. It is important that you remember that I squared equals minus 1, and so the final term, minus 3i squared, equals minus 3 times minus 1, which equals plus 3. You can use this to help collect together the real and imaginary parts of the answer to give z1 multiplied by z2 equals 5 plus 3i multiplied by minus 2 minus I, which equals minus 10 plus 3 minus 6 plus 5 I, which equals minus 7 minus 11i. So the answer is a complex number expressed in Cartesian form with a real part of minus 7 and an imaginary part of minus 11. When you multiply a complex number by its complex conjugate, you get a result that proves to be both important and useful. Example: given that z equals 5 plus 3i, what is z bar? You can write z bar equals 5 plus 3i multiplied by 5 minus 3i, and so z multiplied by its complex conjugate z bar equals 5 plus 3i multiplied by 5 minus 3i, which equals plus 25 plus 15i minus 15i minus 9i squared, which equals 25 plus 9, which equals 36. Cancelling out the second and third terms and using I squared equals minus 1. Multiplying a complex number by its complex conjugate is important and useful because the imaginary part cancels out and the answer is a purely real number. Multiplying a complex number by its complex conjugate gives a purely real number. Using the general complex number z equals a plus bi, z multiplied by its complex conjugate z bar equals a plus bi multiplied by a minus bi, which equals a squared plus b squared. This is the sum of two squares, which is similar to the difference of two squares, a common piece of mathematics discussed in the study guide, factorising quadratic expressions. The boxed mathematics above illustrates how you can factorise the sum of two squares. Dividing complex numbers. Dividing complex numbers is more challenging than their addition, subtraction or multiplication. Let's look at an example to help understand the process. Example: if you have two complex numbers, z1 equals 5 plus I and z2 equals minus 2 minus I, what is z1 divided by z2? You can write z1 divided by z2 equals 5 plus I divided by minus 2 minus I. The difficulty here is that a complex number has a real part and an imaginary part, but in this piece of mathematics it is difficult to see what they are. The method uses the fact discussed in the previous section, that multiplying a complex number by its complex conjugate gives a real number. If you had a real number as the denominator of the division, you can split the complex number up into real and imaginary parts. So you need to multiply the denominator by its complex conjugate, minus 2 plus I, to get a real number. Remember that you must also multiply the numerator by the same thing to keep the fractions equivalent. So z1 divided by z2 equals 5 plus I divided by minus 2 minus I, which equals, after multiplying the numerator and the denominator by minus 2 plus I, 5 plus I multiplied by minus 2 plus I, all divided by minus 2 minus I multiplied by minus 2 plus I, which equals minus 10 plus 5i minus 2i plus I squared, all divided by 4 minus 2i plus 2i minus I squared, which equals minus 11 plus 3i, all divided by 5. This piece of mathematics makes use of many ideas discussed in this guide, such as expanding brackets, collecting together real and imaginary parts of a complex number, complex conjugates, and I squared equals minus 1. You are still not finished, however. To give the answer in Cartesian form, you must separate the real and imaginary parts of the complex number. Z1 divided by Z2 equals minus 11 plus 3i, all divided by 5, which equals minus 11 over 5 plus 3 over 5i, which shows that the real part of the answer is minus 11 over 5 and the imaginary part is 3 over 5. Further guidance and information. If you have any further questions about mathematical skills or would like to discuss any other aspects of mathematics, you can talk to your lecturer or personal advisor or make an appointment to see a Learning Enhancement tutor in the Dean of Students office. You can telephone 01603 592761, email dos.help@uea.ac.uk, or visit our website at www.uea.ac.uk/dos/let. There are further resources on many other aspects of numeracy, mathematics, statistics and science available from the Dean of Students office and on its website. These include questions to practice, model solutions and webcasts illustrating essential skills. This guidance is one of a series on mathematics produced by the Dean of Students office at the University of East Anglia.